In this video, I will talk about Ethernet switches. So recall that in an earlier video, I mentioned that up until the mid-90s or so, Ethernets ran with a bus topology. And beginning with the mid-90s, Ethernet switched to using a star topology with a switch at the center of that star. So let's talk a little bit about what these switches look like. So an Ethernet switch is a link layer device that will take an active role in the network. Ethernet switches will store and then forward Ethernet frames that come. Now they do this by examining the incoming frames and examining the destination MAC addresses and then selectively forwarding these frames to one or more outgoing links when a frame is to be forwarded. Okay, and the carrier sense multiple access collision detection is used to access a segment. Now, all hosts on a network are unaware of the presence of switches. Okay, so the switches are transparent. Like right now, I don't know that I'm connected to a switch. Well, I do because I work in networking, but your machine is unaware that it is talking to a switch. And switches are plug-and-play devices. In other words, they don't need to be configured by a network administrator. And they are self-learning. And self-learning is how they switches selectively forward frames to one or more outgoing links. So here is an example. So every host would typically have a dedicated and direct connection to a switch. Now the switch, as I mentioned earlier, will buffer packets if packets are arriving faster than they can be sent out. And the Ethernet protocol is used on each incoming link, but there are no collisions because there's typically only one host on a spoke of the switch, if you would. And it is full duplex, which means, say, interface B prime can be sending data to the switch at the same time that the switch is sending data down to B prime. So each of these links is a separate collision domain. What that means is that A can be sending data, for example, to A prime at the same time that B is sending data to B prime, and they won't collide at all. So the next question we need to ask then is, how does the switch know that A prime, for example, is reachable via interface 4 and B prime is reachable via interface 5? Well, the answer is that every switch will have a switch table, and each entry of the switch table will contain a MAC address for the host, an interface to reach the host, and some timestamp. This switch table is going to look very much like a routing table. Now, the next question you might have is that, how are these entries created? Because, as I mentioned, switches are plug-and-play devices. So how do these entries get created? How do they get maintained in the switch table? Well, they get built in using something similar to a routing protocol. So this is how it works. A switch will learn which hosts can be reached through which interfaces. So initially, when the switch is powered on, the switch will have no entries in its switch table. So when a frame is received, so let's say A was sending data to A prime, when the switch receives a frame from A, then the switch will learn, oh, the MAC address down here is reachable via interface 1. And so it will now store that information in its table. Now, when let's say it doesn't know where A prime is next, then the switch will selectively forward that frame on all the interfaces except that on which it came in. Why except where it came in? Well, suppose that A prime was also reachable via interface 1, then it is guaranteed that A prime would have already learned would have already received that message. So there's no need to forward that message, say A was trying to talk to A prime, also out of the interface where that frame came in. Okay, so let's look at this illustration. So as I said, when we power on our switch, the switch table is initially empty. So let's say A was talking to A prime, so that frame comes in, and our switch now learns that A is reachable via interface 1. So it records that information in its switch table, and then it will now selectively forward that frame on all interfaces except for interface 1. So here is essentially how the self-learning works. When a frame is received at the switch, you record the incoming link and MAC address of the sending host. Then you index your switch table using the MAC destination address, and if you find an entry for the destination, then if the destination on the segment from which the frame is, if the destination on the segment from which the frame arrived, then you drop the frame. Otherwise, you forward the frame on an interface indicated by an entry in your switch table. Otherwise, you flood it. You basically forward it on all interfaces except the arriving interface. So let's look at this example. Let's say A was talking to A prime. So initially, we will record that A is reachable via interface 1. Now, we don't know where A1 is right now. So we're going to forward it, flood it on all interfaces except interface 1. And so there, flood all interfaces except interface 1. So it so happens A prime will get that. The messages will, that message will also go to B prime, C prime, B, and C. Now, those messages were not destined for those machines, so they will just be dropped. Now, let's say at some point later, A prime decides to formulate a response. So A prime will now send a message going from A prime to A, and that message will go to the switch, and now the switch will learn that, oh, A prime is reachable via interface 4. So now, the switch will index its switch table and say, oh, if you're trying to reach node A, you need to go out on interface 1. So at this point, it will now send that message, that frame, unicast to A. Okay? And so that is just how it works. Now, it turns out that self-learning switches can also be connected to each other. So let's just say S1, that's a self-learning switch. We can connect it to these other switches, S4, S2, S3. So a question you might have is, suppose we are sending from A to G, how does S1 know to forward a frame destined to G via S4 and then S3? Well, the answer is still by self-learning. And self-learning will actually work in exactly the same way as we saw with the single switch case. So let's just say, for example, C sends a frame to I, and then I responds to C. Okay? So what would the switch tables and packet forwarding look like in switches S1, S2, S3, and S4? I'll leave that as an exercise for now, and later on I will show you what the answers ought to be. So here is what an institutional network might look like, say at a campus like UWI. Typically you'd have a gateway router, and then that router may be connected to some switch, and then you might have a bunch of servers and the rest of the network. This is an IP subnet. So this, by the way, is not uncommon for how a network like UWI's, UWI Mona that is structured. So the last thing I want to talk about basically are switches versus routers. It turns out that switches and routers are both store and forward devices. Routers, though, operate at the network layer, so they examine network layer headers. Switches, on the other hand, are link layer devices, and so they examine link layer headers. Both routers and switches have forwarding tables. In routers, these routers will compute these forwarding tables using routing algorithms and IP addresses. In switches, on the other hand, they learn the forwarding table using flooding, self-learning, and MAC addresses. So that brings to an end this video, and in the next video I'll talk very briefly about wireless networks, and then we will talk also very briefly about wireless LANs 802.11. Thank you.